No, I mean, like, she has to say something.
Our mic is.
It's by default. I think it's Spanish.
The microphone is.
Yeah. It's
Hello, can you see me?
Oh, yes, we could hear you. Just 1 second. Perfect. I'm seeing you. Can you see us and hear us properly?
Yes, thank you.
Okay, perfect.
Okay. Just gonna share my screen.
Yes.
Strange. Are you seeing my screen? Sorry? Okay. Let's see, it didn't work.
It's gone. The window is gone.
Yeah. Something strange. Okay, let's try that again. It's saying sharing is paused. You'll need to go back to the window you were sharing to resume. I don't know why it's saying sharing is paused.
Oh, just 1 second, please. No, the window is gone. If you click the share button next to the mic.
Yeah.
And then select the slide window on your device.
That's what I did.
It was just loading, I think, but it's blank. Huh?
Okay.
Oh, it's here, it's up. I'm bringing it to the main screen. Okay, there we go. If you can just click slideshow display, it'll be all set.
Okay. Which view are you seeing? Are you seeing the right view
The
now?
first slide, yes, targeting microplastics and nanoplastics in treated waters.
You're not seeing the notes view?
No.
Okay. Just gonna check something because I don't see you anymore.
Oh, you couldn't see us, I think.
Okay.
With the town hall meeting by default.
Like I don't see the teams anymore. Are you still seeing the screen okay?
Yes.
Okay. And if I switch the slide, do you see the second slide
Yes.
now? Okay. Okay. Well, there it is, maybe. So there's, if I'm not mistaken, there's 6 people online?
Yes, and there will be more when we're still 5 minutes ahead.
Pardon me?
Yes, there will be more joining.
Okay.
We're still early, like 5.
It's actually really nice. I know. Also, today's like pretty nice weather for you. I mean, no, it's cold for you. It's nice weather for me. Guys, look. Guys,
Also, so we'll also get this.
Before.
uh-huh. So that's good. Yeah, lessons. Oh wait, you do.
Yeah, you see people try to join.
Oh, yeah. You forget.
Sometimes you don't wear it.
You're kind of like.
Wait, did you see my outfit? Good morning, everyone. It's like speckled.
Yeah, that's pretty. Okay, Jenna, we need one.
You're growing,
Good images. Or just.
you're growing.
Yeah, it's nice.
The boardroom is going to be so.
Thanks, that's enough.
Or they doctor.
How are you?
Yeah.
The doctor was perfect.
But that's the old,
Yes.
And after.
she had to come early to move the plate.
But the storm stuff was that.
Okay, hello everyone, and welcome to the United Nations University Institute for Water, Environment and Health Science Talk Series as we celebrate our 30th anniversary year. My name is Lu Yingwang, UNU-INWEH's Public Outreach and Education Associate, and I'm delighted to be your host for today's Science Talk. For those of you who are joining us for the first time, our Science Talk showcases the diverse policy relevance and interdisciplinary research of UNU-INWEH and our global network of experts. These sessions are designed not only to share cutting-edge science, but also to explore how that science translates into real-world solutions for water, environment, and health challenges around the globe. Today's session, like all of our talks, is being recorded. The video would be made available in an open access format following the event. And you can find recordings of all previous science talks on demand via our website and YouTube channel at UNU/INWEH/science-talks. We're also pleased to introduce a new YouTube live streaming option starting from today, making it easier for everyone to join our science talks. There is no need to register to watch live. Simply go to the UNU-INWEH YouTube channel and click on our profile picture to access the stream. As always, we will conclude with an interactive Q&A session. So please feel free to post your questions in the chat at any point during the presentation, and we will address as many as possible towards the end of today's session. Today's Science Talks is entitled Targeting Microplastics and Nanoplastics in Treated Waters, a Sustainable Technology for Removal of Microplastics and Nanoplastics in Contaminated Waters. And it is my great pleasure to introduce today's speaker, Professor Nathalie Tufenkji. Professor Tufenkji's research focuses on environmental nanotechnology, water quality, and development of innovative approaches to address emerging contaminants. In this science talk, she will introduce a sustainable water treatment technology designed to enhance the removal of microplastics and nanoplastics from contaminated waters. Her presentation will highlight the use of reusable functionalized cellulose fibers as a novel treatment approach. These fibers act as superbridging agents to improve particle aggregation and removal. While reducing reliance on conventional chemical inputs, her work demonstrates the potential for this technology to improve treatment efficiency, reduce environmental impact, and support more sustainable water management practices. Please join me in welcoming Professor Tufenkji for today's science talk. The floor is yours. Please go ahead, Professor.
Thank you very much, Lu Ying, for the introduction. I'd like to thank you for the invitation to present within your Science Talk series. It's very exciting for me to have this opportunity to share with you today some of the work that we're doing in my laboratory at McGill, as well as with my collaborators at other institutions, including l'École de Technologie Supérieure de Montréal. So in my talk today, I'll be telling you about some of the work that we've been doing on this, as you mentioned, developing technology, sustainable approach to target certain contaminants, including microplastics and nanoplastics. So a little bit of background, I'm a professor of chemical engineering at McGill University in Montreal, Canada, and I'm also an adjunct professor of water quality and plastic pollution with the UNU Institute for Water, Environment and Health. Okay, so in this figure here, I'm showing you some of the different contaminants of concern that we deal with in urban environments. And so if I can use this laser pointer here, which hopefully you can see, you know, where some of these we've been aware of for decades, including hydrocarbons, metals, as well as fire retardants, and other kinds of contaminants we're becoming more concerned with more recently. For example, tire wear particles, microplastics that arise from the breakdown of bulk plastic litter, And you, of course, as you all recall, during COVID and post-COVID, where we wear masks, these masks are made of plastic, and we find them very often, at least during COVID and post-COVID, we found them littering urban and other environments, and where they could break down and release plastic microfibers. So clearly, there's a growing matrix of contaminants of emerging concern. And so there's a need for us to develop novel approaches to manage and handle these various contaminants of concern. So in this figure here, what I'm showing you is just the conventional water treatment process. And so many of you are probably very familiar with this process, but I'll just go over it for those of you who might be less familiar. So in conventional water treatment, we have our water that we want to treat that contains our contaminants, and we're going to add a coagulant that is going to essentially have these contaminants come together and form small clumps that we call coagula. And then we're going to add our flocculant, which is going to then flocculate those little clump coagula into larger flocs. So we want to aggregate all of this material, all these contaminants into these large flocs. And the idea is that we'll then allow time for those flocs to settle down from the treated water and form a sludge at the bottom of this, what we call our settling tank. So because these flocs are actually not so large, in fact, so they typically take quite some time to settle. And which is why we actually need a very, very large settling tank. So this is one of the issues that I want to highlight in the conventional treatment process, is that it actually has quite large of a footprint, especially with respect to this settling tank, which is quite large, takes up a lot of space, has a high capital cost. Also, like I mentioned, we are using continuously these single-use chemicals. So the coagulant and the flocculant are single-use chemicals that we're using throughout the process to treat wastewater or to produce drinking water. So in all of these cases, these chemicals are ending up in the sludge that will end up at the bottom of our settling tank. So these are the kind of the issues that we're dealing with in the conventional treatment process, and that we wonder whether we can address these issues with a novel strategy. So when we started this work, we asked ourselves, can we improve the conventional treatment strategy or efficiency while reducing the usage of chemicals? So in order to make the process more sustainable. So a few years ago, I had a postdoctoral fellow working in my laboratory, Dr. Mathieu Lapointe, who's now a professor at École de Technologie Supérieure de Montréal. And we continued to collaborate on this research. But when Mathieu was pursuing his postdoctoral fellowship in my laboratory, we observed that we can create these super flocs by adding cellulose fibers during the treatment process. So here what I'm showing you at the top is the size of a conventional floc. This is a microscope image of the floc. So you could see it's about maybe 1/3 of a millimeter, almost less than 1/2 millimeter. And then you can see here a super floc that is formed when we add cellulose fibers during the process, during that flocculation process. And you can see how much larger this super floc is, 10 to 15 times larger than the floc you'll obtain with coagulant and flocculant alone. So what is the implication of forming these super flocs? Well, I mentioned to you that what we're dealing with when we're dealing with water treatment, we form these flocs, we want to give them time to settle out of the solution. And so what we can see here, just as an example, this is an experiment we do in the lab to look at the settling of these flocs. Here's the conventional treatment where we have just coagulant and flocculant, and we've allowed the flocs to form, and we've given a certain amount of time for those flocs to settle. And you can see there's still a lot of flocs in the suspension that haven't had enough time to settle down to the bottom of the beaker. But on the bottom image, what you can see is the water that's been treated with the addition of fibers. So some coagulant, some flocculant, as well as some of these cellulose superbridging fibers. And what you can see is that in the same amount of time, those flocs have really settled down much faster. You can see that accumulated sludge at the bottom of the beaker. And you can see how much clearer the water is. when we've added the fibers. So clearly this addition of fibers, these are cellulose fibers, which is natural. We can also obtain them from just recycled paper, recycled fibers. But you can see what a great difference it makes in terms of the formation of these superflux and the rapid settling of those superflux. So we decided to explore this further. We were very excited by those initial results. And let me show you a little bit some of the results that we obtained. So here what I'm showing you is the settled turbidity. So when we do these experiments that I showed you here, we're essentially measuring the turbidity of the water after the settling. So then essentially we call that the settled turbidity. So we can measure the turbidity at the beginning of the experiment where it would be more turbid, something like you see on the top image. And then we measure the turbidity again at the end of the experiment where the water theoretically should be more clear. So essentially this is what I'm showing you here in this graph. I'm showing you the settled turbidity as a function of the settling time. So how long we wait and how long we give those flocs time to settle. And here this experiment was done with 100 milligrams of fibers per liter. And I'm showing you in red the results when we have no fibers, so just those coagulants and flocculants. And then you can see that it takes, after 3 minutes of settling, we've reached our target turbidity. In this case, this is for a drinking water application. We were aiming for a target turbidity of 1 NTU, which is the units for the turbidimeter. So you can see here there's a dashed line, and I'm showing you that after about 3 minutes of settling with the conventional treatment, we can reach about 1 NTU. And if we give more time, the turbidity will drop even further. But what's very surprising here is how the turbidity drops very fast when we add some fibers. So you can see here in blue that after less than 30 seconds, we've pretty much reached this 1 NTU. I mean, we really go below the 1 NTU at 1 minute, but you can see just how fast that turbidity drops when we have fibers. So we're making these super flocs. They're settling much faster. Practically speaking, what does that mean? It means, we can essentially operate with a much smaller settling tank. We just don't need as much of that settling time to reach our target water quality. So this has very interesting implications for the fabrication, the construction of new treatment plants, because you can essentially construct a much smaller settling tank. But we were very curious to see, well, with this improved performance, could we actually decrease the amount of chemical that we're using during the treatment? So the amount of coagulant and the amount of flocculant. So here again, I'm showing you the settled turbidity, but instead of showing you as a function of settling time, here I'm showing you at a fixed settling time, but we're varying the coagulant concentration, in this case, alum. So we're showing you in milligrams of alum per liter. And in red, again, I'm showing you the conventional treatment, so just coagulant and flocculant, so alum and PAM. And then you can see here that we have our turbidity, our settled turbidity is dropping, and we reach our 1 NTU target, almost reach it at about 50 milligrams per liter alum. But when we add these fibers, these cellulose fibers during the procedure, we can see that we can actually reach this 1 NTU target at a much, much lower coagulant dose. So this is very interesting because now we can actually decrease the amount of single-use chemical that we're using with, tons of these chemicals to treat the water. So this is going to make a big difference, not only for operating costs, but also the sustainability of the process in terms of these chemicals ending up in the sludge. Likewise, we can look at varying the dose of flocculant. In this case, it's PAM, polyacrylamide. And you can see here again in red, when we don't have the fibers, so we just have coagulant and flocculant, and we can see that we have our 1 NTU target in gray. We haven't even reached it yet at 0.5 milligrams per liter PAM, but we can, when we add fibers, we can see that we can reach that target value even as low as 0.2 milligrams per liter PAM. So this is very interesting. It shows us that we can actually decrease the coagulant dose and the flocculant dose because these super bridging fibers accelerate floc maturation and enhance the settling of these flocs. And so this would reduce our reliance on these single-use chemicals. I forgot to ask, I hope everyone can hear me okay. And hopefully you would have raised your hand if you're not hearing me clearly. Okay, so I showed you how, we explored this new technology in terms of adding these super bridging cellulose fibers to create these super flocks. And for decades, engineers, water treatment engineers have really focused their efforts on improving this floc settling velocity. Can we get higher floc settling velocity so that we can improve the treatment performance or process more water? And what if I told you that with these supersized flocks, we actually might not actually need to rely on floc settling any longer? So let me tell you about this and what I mean by this. So we've created, as I mentioned, these supersized flocks. Now these flocks are so large that we thought, okay, well, we can actually remove the flocks from the treated water using a screen. Instead of waiting for these flocks to settle out of the suspension, well, we could just continuously like sieve, if you will, or screen these super flocks out of the water. And this would allow us to just basically save time. We would no longer be relying on this settling velocity. Now you can't do this with the conventional approach. Here I'm showing you the conventional flocks, which would just pass through the screen. So this is not an approach that has been explored before in conventional water treatment, but we figured that maybe with the addition of these fibers, because we're creating these supersized flocks, we could explore the opportunity of removing them using a screening approach, which would be quite cheap and quite rapid. So let's see how we did this. Well, in the conventional water treatment approach that we do at the bench, we use these jar tests. Like I showed you, we have a beaker. We are mixing the water with the coagulant, the flocculant, form these flocks, and then we give it time to settle out by stopping the mixing. So now in our new approach, what we're doing is we'll do our jar test, but then we're going to add these screen baskets inside the water, and basically the flocks will be excluded from the basket, and then we're sampling from inside the basket. So this gives us an idea of essentially what we call the screen turbidity. So here we have what we call the settled turbidity, as I've been showing you in the previous graphs. But now we're going to explore what happens if we actually try to screen these flocks. So screen them, remove them, and then we're going to sample from inside this basket and just basically be sampling what passes through the screen. Okay, so here I'm showing you the screen turbidity. So essentially, whatever turbidity is passing through the screen. And I'm showing you that as a function of the screen mesh size, because we can make these baskets having different screen mesh size. And that's what I'm showing you here on the x-axis. So what you can see here is when we have no fibers, so the conventional treatment, you can see that the screen turbidity actually gets really high at coarser mesh sizes, which makes sense, right? So we have these small flocks, they're getting through the screen. If we really make the screen mesh size very small, so very tight screens, then we can trap those small flocks that we form with the conventional treatment, and we could reach our target of 1 NTU. But what's interesting is once we've added these cellulose fibers, you can see that we can trap those flocks even with very coarse screens up to 2000 mesh size, 2000 micron, and probably up to 3000 micron here, missing some of the experimental data points. But you can see from the trend that you can capture these or exclude these very large super flocks using a much coarser screen. And this is important for us because when you have a very tight screen, it will clog very fast, and that's going to affect the flow of your process, right? So we want to make sure that screen mesh size is as coarse as possible, that it will trap the super flocks, but not completely clog the screen, and that it'll be easier to clean also when we want to do like a backwash to clean that screen. So the idea here is I mentioned to you that we might not actually need a settling tank. And that's what's exciting here about being able to screen these supersized flocks. They're so large that we actually no longer rely on the settling velocity, which was the key principle, the key factor on which we design our process. So now, rather than designing based on the settling velocity, we're essentially just designing based on the size of the floc. And so here, if you could imagine where you have your coagulation and flocculation tank, you can actually imagine a screen, a rotating screen directly inserted inside the flocculation tank, which would screen out these supersized flocs. Remove those flocs from the treated water, you no longer need an actual settling tank. So that would make a massive difference in terms of the capital expenditures and the footprint of any new fabrications of water treatment facilities. So far I've showed you how we can form these supersized flocs using cellulose fibers. And these supersized flocs are so large that not only do they allow us to reduce the coagulant dose, the flocculant dose, but we can also explore alternative ways to separate these flocs from the treated water using, in this case, a screening strategy. But when we got to this point in our research, we asked ourselves, can we do a better job of dealing with classical contaminants and contaminants of emerging concern and still maintain the process efficacy? So moving forward, I'd like to tell you about some work we've been doing where we're trying to actually now functionalize the cellulose fibers, so modify them in a way that would allow us to capture different contaminants and more of these contaminants. So when we first set off to try and functionalize the cellulose fibers, we tried a very simple approach of just grafting some iron hydroxides and oxides onto the cellulose fibers. Now, cellulose is a great platform material because it's quite easy to functionalize with different kinds of chemistries. But when we first started on this, we thought, let's put some iron oxides, some iron oxyhydroxides, which would present essentially positive surface charges on the surface of the cellulose. The cellulose is negatively charged, many contaminants that you'll find in water are also negatively charged. So it's not an ideal surface chemistry to trap those contaminants from the water. So we thought if we could put some metal oxides on the surface of the cellulose fibers, maybe we can trap these negatively charged contaminants from the water. So that's what I'm showing you here. We start with our cellulose fibers and we do some really simple chemistry to get some iron oxyhydroxides and iron oxide little patches on the surface of those fibers. So here you can see a microscope image that shows you these little orange or reddish patches, basically like, think of it as rust, right, on the surface of these cellulose fibers. And we did some tests. These iron oxide patches actually stay on the surface of the cellulose. They're not very easily washed off. So here you can see some electron microscopy images, so much higher magnification. This is a 5 micron scale bar. You can see part of a cellulose fiber that has these patches on them. And you can see here, we can do some elemental analysis that tells us what kind of element we have in different parts of our figure or of our image. So you can see where we have carbon, you can see where we have oxygen, and you can see that we clearly have iron directly on this little patch here of iron oxide. We can also do some XPS analysis, which basically, again, allows us to do some elemental analysis of the surface of these fibers. And you can see that when the fibers are pristine, we only see carbon and oxygen, essentially. And then when we add the iron grafting, we can see that we've actually detected that iron on the surface of the fibers. So we know we have these iron oxides. They're on the surface of the fibers, but does it actually help? So here we need to do some jar test experiments to see whether these iron oxide modified cellulose fibers actually make a difference. So what I'm showing you here is DOC removal. So DOC in milligrams per liter as a function of the fiber concentration that we're adding in our experiments. So when we have no fibers here on the y-axis, this is just the conventional treatment. So we have 2 examples here, the 20 milligrams of alum per liter, and you can see the DOC levels are higher. Or if we add 40 milligrams of alum per liter, we can see that we can drop that DOC quite significantly. If we have 30 milligrams of alum per liter, we can see we land right around 3 milligrams per liter DOC. But now we can also start adding some fibers into the mix. And we can see here that with 100 milligrams per liter fiber, well, now we've reached the same DOC level that we had with 40 milligrams of alum per liter alone. We've reached that, but now we only need to use 30 milligrams of alum per liter. So you can see how the addition of the cellulose fibers, which is a natural material, it's cellulose, you can see how it's helping us to reduce the contaminant dosage, the chemical dosage here of alum. And you can see here with that 30 milligram of alum per liter, how we keep dropping the DOC as we increase the fiber concentration. So the fibers are helping to trap the DOC. We were also interested in phosphorus removal. So here I'm showing you the phosphorus reduction in milligrams per liter now as a function of the alum dose. So I'm showing you this for two conditions. Well, when we have no fibers, so the conventional treatment, and we can see that we need to increase the alum dose to about 40 milligrams per liter to reduce the phosphorus load by 3 milligrams per liter. But we can reach that same performance with a much lower alum dose when we have fibers. So those fibers also help to trap the phosphorus. So we're removing DOC, we're removing phosphorus. My lab really does a lot of work on microplastics and nanoplastics. So we were interested to see, can we remove nanoplastics? So here's one example with 20 nanometer. These are tiny, tiny polystyrene particles. And I'm showing you here the nanoplastics removal. And we can see that with the conventional treatment was not very effective at removing nanoplastics. We could reach maximum of around 45%, 50% nanoplastics removal. But when we added these iron grafted fibers in the procedure, we can see now that the fibers really improve nanoplastics removal. So it's a technology that not only acts as a super bridging agent to form these super flocs, but also as an adsorbent to remove the dissolved and particulate contaminants. So this was the work that we had done when we first started trying to functionalize the cellulose fibers. But more recently, we tried to look at alternative approaches to functionalize the cellulose. There's many different ways you can perform chemistries on cellulose to impart different functionalities on the surface. And so here I'll give you an example of one approach that we carried out recently, just recently published in Separation Purification Technology. So here first we start with our pristine cellulose, and we're going to oxidize the cellulose. And we're going to take that oxidized cellulose and we're going to modify it with quaternary ammonium on the surface. So we're going to create these quaternary ammonium groups on the surface to give that cellulose some positive character. Okay, so like I said, the cellulose is mostly negatively charged, and now we're putting some positive flavor on the surface of that cellulose so we can trap our contaminants. So when we do this chemistry, we were curious to see how it might affect the cellulose. You can see here first we're looking at basically the length of the cellulose fibers to see when we do this chemistry, do we lose, are the fibers shortened? We can see the fiber length distribution is quite stable. So we did these chemistries for different oxidation times. Here we're doing the oxidation 30, 60, 120 minutes. And you can see that the fiber length distribution pretty much stays the same. So we're not breaking the cellulose fibers. We can also measure the surface charge of these cellulose fibers. And this is what I'm showing you here. You can see the pristine fibers, as I mentioned, they're negatively charged over a very wide here pH range. So from 7 to 8.5, you can see these fibers are negatively charged. But now as we start modifying them, putting these quaternary ammonium groups on the surface of those fibers, you could see that they start becoming more and more positively charged, or if we could say less and less negatively charged. So that's interesting to us because now we wonder, okay, these fibers, well, how will they perform in our water treatment process? Okay, so when we did this, we were, I'm not showing you all of the data, but we did do some optimization, and we did figure that one of these oxidation times was the optimal one. And if I'm not mistaken, it was the 60-minute oxidation. So what I'm showing you moving forward was done with those 60-minute oxidized fibers. So what I'm showing you here is some jars where we did these jar tests. So here you can see this initial jar. So at the beginning of the experiment, you can see the turbidity is 62 NTU, so quite high. This is a synthetic wastewater that we prepare in the lab. So we prepare synthetic wastewater, allows us to have more consistency throughout our different experiments. Now we can treat that wastewater using the conventional approach. You can see that after a certain amount of time, the turbidity is 25 NTU. So pretty good. But we can also add some fibers, and we can see that we could drop down, in this case, to 17 NTU. And you can see these huge super flocks here settled at the bottom of the beaker. Now, the last image shows you the water that's been treated with our modified fibers, these quaternary ammonium modified fibers. And now you can see the turbidity has dropped down to 3 NTU for the same amount of fibers that were used with the pristine jar. So this here, down here, what we're showing you, some microscope images of these flocks. Like I said before, the conventional flocks are quite small, you can see here, but with the pristine fibers, excuse me, you can see we formed the super flocks that I showed you earlier. But now with these modified fibers, we found that they form flocks that are actually 2 times larger than what we form with the pristine fibers. So these modified fibers are really forming super flocks. And this explains, how we're getting this really clear water here with the modified fibers. So I'll show you here just some experiments that we try to explore how robust these modified fibers are in terms of their treatment performance. So what I'm showing you is the settled turbidity, but as a function of pH of the water that we're treating. You can see the conventional approach, just using alum and PAM, you can see that it kind of breaks down as you increase the pH. And this is well known. This conventional approach doesn't perform well at higher pH. You can see that when we add pristine fibers, so just unmodified fibers, you can see that it performs better than the conventional approach, but still at the very higher pHs. We're not quite reaching our target turbidity of, in this case, 25 NTU, because this is a wastewater treatment application. So the treated water has a higher turbidity. And finally, in red, I'm showing you the results with the quaternary ammonium modified fibers. And here you can see that the performance is really very robust, wide range of pH, really low settled turbidity, less than 5 NTU from what I can see in the graph. We also explored what happens if you have a really highly turbid wastewater. You're starting off with a very turbid wastewater. So here in this case, we started with 62 NTU, but let's see what happens when we start increasing that initial turbidity up to about 275 NTU. You can see here that the conventional approach breaks down. It can't keep up with all of that turbidity. Likewise, the pristine fibers don't reach our target turbidity at these higher turbidity levels. And then finally, our modified fibers, you can see here that the turbidity, the settled turbidity really stays very low. We're able to reach, much below our target turbidity of 25, even at really high starting, very dirty waters. So essentially that's what this is showing you. Even if your water is super dirty, you can still remove a lot of that turbidity using these modified quaternary ammonium modified fibers. Okay, so I showed you earlier how we're interested in exploring whether the addition of these cellulose fibers could enable us to actually reduce the chemical usage. So we decided to explore this as well with our new cationic quaternary ammonium functionalized fibers. So let me show you the results here. I'm showing you the turbidity. This would be the settled turbidity as a function of the flocculant concentration. So here we're using PAM. I'm showing you the results of the conventional treatment. These are the triangles with no fibers. And you can see that as you increase, you have a starting turbidity of about 62. And as you increase that flocculant dose, you can see that the settled turbidity is dropping as we would expect. And our target turbidity here is 25. So of course, this is a wastewater treatment application. And you can see that we can reach our target turbidity when we have a flocculant dose of 0.5 milligrams per liter. Now, we can also add some pristine fibers, as I showed you before. When we add the pristine fibers, we reach that target turbidity at a much lower flocculant dose. You can see we can reach it right around here. We can reach that target turbidity much better than the 0.5. So like I showed you before, that these fibers can allow us to reduce chemical dosage. But what's really interesting is when we add these cationic fibers, and we did this with two different coagulant doses of 30 and 50 mg per liter of alum. You can see the results here. We are reaching our target turbidity over the entire range of flocculant concentration and even without flocculant. So this shows us that we can actually, in this case, completely eliminate the need for the flocculant because these functionalized fibers are actually serving to replace that flocculant. So that's very exciting. We can use zero flocculant. We still have some alum, of course, to form those small coagula. We can also explore the impact of varying the coagulant concentration. So here we're keeping the flocculant concentration constant, and we're just varying the coagulant concentration. And it's very much the same picture where, well, in this case, without fibers, we need to use a really high coagulant dose here to reach our target turbidity. Likewise, even with the pristine fibers, we need to use quite a high coagulant dose, but we can achieve our target turbidity with a much lower coagulant dose when we have our cationic fibers. So you can see that here we can drop down to 10 milligrams per liter alum when we add these cationic fibers. So these cationic fibers are very effective at removing our suspended solids, and especially at very low chemical doses. And in this case, we saw that we completely eliminated actually the need for the flocculant. So as I mentioned before in my lab, we really do focus a lot on microplastics and nanoplastics. So in this case, Masashi, who's the postdoc in my lab, was working on trying to understand whether these cationic fibers could effectively remove microplastics and nanoplastics. So there's a lot of data in this graph, and I'll just draw your attention to the main data points that I want to highlight. So here we're looking at the removal efficiency of microplastics and nanoplastics. So the microplastics are 1 micron, they're the red triangles, and then we have two sizes of nanoplastics, 200 nanometers in yellow and 20 nanometers in green. So here at the bottom, you can see that when we have no fibers, so just the conventional treatment, we remove about 30% of the microplastics and nanoplastics. So not a lot. We still have a lot of micro nanoplastics in the treated water when we're just using coagulant and flocculant. This is a problem that water treatment plants globally are going to struggle with in terms of removing microplastics and nanoplastics. We can see it here. The conventional approach is not handling those micro nanoplastics very well. Well, of course, this is one type of chemistry of plastic, would need to be explored with other chemistries, but at least with this first model polystyrene, we don't see very effective removal. So we started looking, okay, what happens if we add fibers? So here the pristine fibers, you can see you get some better removal of the 1 micron, but still not very good removal of the nano. We can start adding these cationic fibers. When we add these cationic fibers, now we see a huge jump in the removal of microplastics and nanoplastics. And we can start increasing the concentration of those cationic fibers. We do see some improvement here at 200 milligrams per liter of the fibers, not much of a change at 250. So fine, we see that, we can use this as our base case scenario, our foundational scenario, 150 milligrams per liter of the cationic fibers, and this is why it's in gray. And here, Masashi used 50 milligrams per liter of alum and 0.5 milligrams per liter of PAM. So that's his baseline scenario. And then he said, well, what if I drop my coagulant dose? Can I drop the coagulant dose? So this is what he's looking at here. You could drop the coagulant dose, but in case I should mention, he also dropped the flocculant dose quite a bit from what he used here. From 0.5, he went down to 0.2. You could see the performance dropped, but when he maintained the coagulant dose, you could see that the performance is still very much the same as what he got with the higher flocculant dosage here. So here we use 0.5 mg per liter PAM. Here we only use 0.2. So less than half the flocculant, still the same removal of the particles. So that was quite exciting here. We can see that we can actually, again, drop that dose of chemicals. And finally, we started exploring what happens if we modify the timing of addition of these fibers. So we were always adding them kind of near the end with the flocculant. We said, what if we add them before the coagulant, after the coagulant, at different times? So basically the dosing schedule. And so Masashi did this for different dosing schedules and identified an optimal dosing schedule, which you can see here just by modifying the timing of addition of the fibers. You can see that he improved his nano and microplastic removal efficiency compared to the baseline case. And here you can see that he's reduced the coagulant dose compared to the baseline and less than half the flocculant dose compared to the baseline. So there's still, of course, optimization we can do, but we're moving in the right direction. We can see that we went with the conventional treatment from removing essentially 30% of the micro nanoplastics to removing almost 100%. So really high levels here, higher than 90% removal. And meanwhile, still decreasing the coagulant and flocculant doses. So let me show you what these flocs look like after treatment. In this case, our polystyrene beads are fluorescent, so we can actually image them and see where they land on our flocs. So what we're showing you here is some flocs where the flocs were formed with these cationic fibers. And you can see that there's fluorescence everywhere on the fibers. There's fluorescence in the flocs that are formed here, these coagula, but also everywhere on the fibers. And that's because these polystyrene beads are negatively charged. The fibers have some positive character, so the beads are attaching all over those fibers. When we use the pristine fibers, you can see here, we see the fiber in the microscope, but we don't see any particles. And that's because they're negatively charged fibers, so the particles are not drawn to the surface of the fiber. They are only being captured in the coagula. Okay, so very different mechanisms when we're working with this cationically functionalized cellulose fiber. Just a few more slides here before I finish. Just wanted to show you a question we get asked very often is what happens to these fibers when they end up in the sludge? Well, we've been exploring the reuse of these fibers. So recovering the fibers from the sludge and then reintroducing them in the coagulation flocculation step. So here we're showing you an experiment where we're looking at the removal efficiency of turbidity and the beads. After one cycle, you have pretty much 100% removal efficiency. And then we can capture those fibers from the sludge. We don't even treat them. We just put them right back in and we reuse them. And you can see that the turbidity removal stays very high. The microplastic removal stays also very high. Nanoplastic removal drops a bit, drops down to about 80% after 5 cycles. Obviously, there's some optimization to be done here. We could look at exploring rinsing the fibers, treating the fibers before reusing them. But there is a potential here to recover the fibers and reuse them, which of course would make the process more sustainable. Okay, so up until now, I've told you about this treatment strategy that we've been developing using cellulose fibers. And I'm showing you how we can quantify, I was showing you how we can quantify the removal of microplastics and nanoplastics. But in fact, I should admit that we cheat a little bit in our micro nanoplastic removal measurements. And what I mean by this is, like I said, we're using fluorescently labeled particles. This is because it's actually really, really difficult to measure nanoplastics and even microplastics in treated waters or raw wastewaters. You're essentially looking for a tiny carbon-based particle in a dirty water. So it's very, very challenging. And this poses a huge challenge for water treatment operators. How can we expect them to actually quantify the amount of nanoplastics and microplastics in dirty water when it's challenging for us to do this even in clean water? So this is why we use these fluorescently labeled particles, because it allows us to measure indirectly the concentration of particles by measuring the fluorescence. So we asked ourselves, can we come up with a way to facilitate the measurement of nanoplastic, microplastic removal in water treatment processes globally? Can we make it easier for water treatment operators to quantify how much micro nanoplastics they're removing? What we did is we did many, many jar tests, as you can see here in the laboratory, looking at microplastic and, in this case, nanoplastic removal. So this is nanoplastic removal. And what we did is we plotted the nanoplastic removal as a function of the TSS removal, so total suspended solids. TSS is something that water treatment plants measure all the time. So we thought, wonder if they're already measuring TSS, can we relate that somehow to nanoplastic removal? And in fact, we did these experiments over a very wide range of conditions. So we did this for different coagulants, nanoplastic sizes, nanoplastic chemistries, nanoplastic surface charges, and aging history. We used different separation methods. We used different wastewaters. So the wastewaters we use synthetic wastewater, municipal wastewater, activated sludge water, water from an aerated lagoon. So we really tried a lot of different conditions. And we plotted all this data as a function of nanoplastic removal as a function of TSS removal. What we saw is all of this data kind of fell on this curve. And you can see there's a really, really strong correlation with an R-squared of 0.9 that relates nanoplastic removal to TSS removal. So we actually developed a correlation that allows us to kind of try and predict how much nanoplastic removal you might expect if you have X amount of TSS removal. So based on this correlation, we can predict that for a given initial concentration of TSS in your water treatment process, in order to achieve a certain regulatory limit of 25 milligrams per liter TSS after treatment, you can expect a certain range of nanoplastic removal. We can predict that range. So depending on where you're starting in terms of your TSS, we can predict how much nanoplastics you might remove. And typically you might expect between 40 to 70% nanoplastic removal if you're following typical North American TSS removal regulations. So we think this is a step in the direction of trying to support water treatment plants in their monitoring of nanoplastic and potentially even microplastic removal. Of course, it doesn't replace measurement of nanoplastics or microplastics, but it's one tool that they could use to try and understand the extent of nanoplastic removal in their system. So just to summarize what I talked about today, I showed you how cellulose fibers can be used to replace a portion of single-use coagulants and flocculants in water treatment while still improving the treatment capacity. I showed you how we can functionalize cellulose fibers to target certain contaminants, but still a full technico-economic analysis is required to evaluate the feasibility of full-scale implementation of our technology. I showed you how nanoplastic removal can be estimated by measuring TSS removal. And of course, more research is needed to develop more advanced methods to allow us to quantify nanoplastics, microplastics in raw and treated waters. So I'd like to acknowledge the postdocs and students who conducted this work, who collaborated with me on this work. Mathieu Lapointe, who was a postdoc in my lab, is now a professor at ETS, and we continue to collaborate on this project. The funding agencies, as well as our industry partners, Camira Water Solutions Canada. And of course, thank you again for the invitation. I'm so happy to share with you the work that we're doing, and I'm happy to answer any questions.
Thank you, Professor Tufenkji, for this fascinating presentation. You highlighted that microplastics and nanoplastics represent not only a detection challenge, but also a treatment challenge, especially as these contaminants become more widespread in aquatic environments. I'd like to start by one of the three questions we have in the chat box. So one of the anonymous users been asking, when ferric iron is used as the coagulant, how does it performance compared with grafting iron onto cellulose? Sorry, you're muted. I think.
Sorry, I don't see the question in the chat and I didn't quite hear the question
I'll
completely.
repeat it, no problem. So when ferric iron is used as the coagulant, how does its performance compare with grafting iron onto cellulose?
Oh, in this case, I did not show any results with the ferric coagulants in our experiments. And I'm trying to remember if we did any experiments like that. I don't recall. So I don't have an answer to that question because I don't think we explored that.
Okay. Great. So the second question is from Jihan. What concentrations of microplastics and nanoplastics are used to test the performance?
Yeah, and that's a good question. In this case, we have to use quite high concentrations. Again, it's a question of the detection limit, which is very challenging. So we did use quite high concentrations, and in future work, that's going to be our objective, is to try and drop those concentrations to be more realistic, right? Because that will very likely impact the outcome.
Thank you, Nathalie. The last question is from Rima. Do you experience any sort of abiotic degradation of the micro nanoplastics followed by a change in the size population of the MNPs, which might further change the coagulation and flocculation probabilities on the basis of their sizes?
Sorry, Luyin, can you please start the question? I didn't hear the beginning of the question.
Yes, it's very long. Do you experience any sort of abiotic degradation of the micro nanoplastics followed by a change in the size population of the MNPs, which might further change the coagulation and flocculation probabilities on the basis of their sizes?
Yeah, that's an interesting question. I mean, in our experiments, there's no biotic activity to, these are also very, very short experiments, like you saw, just a few minutes. So I don't really expect that to be the case during the treatment process. I mean, maybe before the actual microplastics enter the water treatment facility, then there's time while, these micro nanoplastics are in the environment, in natural waters or in wastewaters, then there might be more time for such breakdown. And it's probably a combination of factors, not just biological degradation, but also physical degradation, physical weathering. So during the actual treatment process itself, I don't expect that kind of process to occur.
Thank you, Nathalie. We also have some questions coming from our boardroom. So starting from Dr. Rin.
Thank you, Professor, for your amazing presentation. My question is about your perspective and your opinion on how this technology would be helpful to feed the policy decision in terms of regulations when it comes to microplastics and the nanoplastic or banning of those materials.
Yeah, it's a good question. Well, thank you for your compliment. Thank you for your interest. I think it's a very challenging question in terms of, I don't think we're going to completely eliminate micro nanoplastics. They're there, and now we just have to deal with them. So we have to find ways to remove these micro nanoplastics as much as possible from either surface waters that are used for drinking water production or from our wastewaters when they're being treated and then disposed of in natural waters. So I think there is a need to optimize treatment processes to remove as much as possible of these micro nanoplastics. And also there's a need for us to develop advanced strategies to really be more confident in the quantification of these micro nanoplastics in raw and treated waters. So it's going to be very hard to regulate without having very reliable and robust measurement techniques. So the measurement techniques really have to be developed so that governments can regulate these contaminants. I hope that answers your question.
Thank you.
Thank you, Nathalie. And we have two more questions from online. The first one, can measuring TSS, I think stands for total dissolved solids, be used as a proxy or indicator for MNPs in water as a routine monitor of water quality?
Yeah, that's essentially what we're proposing with that work. Is we're proposing that at least as a starting point, TSS removal can be used as an indicator of nanoplastic removal. We didn't find as good a correlation with microplastics, but we didn't have as much data with the microplastics. So we have to do more experiments to understand whether there's as good a correlation between microplastic removal and TSS removal. But clearly with the nanoplastics, we saw a very strong correlation.
Thank you. And the next one, how do you recover the fibers from the sludge?
Yeah, so that's a great question. I mean, in this case, it was literally just collecting the sludge and then pulling out the fibers and reusing them. There's different ways. In the past, we've tried some different approaches to like rinse the fibers and treat the fibers. So there's different ways we're going to explore in the future. But the data that I showed there was like no treatment. We literally just took the sludge, separated, just pulled out the fibers and put them back in with the next cycle of treatment.
Thank you. And my last question, what do you feel are the biggest weakness of the current measurement techniques? Which would you recommend as current best practice?
Yeah, I mean, the biggest, I guess, challenge is really, the detection limits. Basically, there's a lot of interference with all the other organic material in the water that is interfering with our measurement of our micro and nanoplastics. So that's a huge challenge. And then, of course, just the how many samples, the throughput, right? How many samples we can process with water, this volume of water that we are treating. We really need to sample larger volumes of water for micro nanoplastics analysis because the concentrations, they're relatively low, right? Relatively speaking. So you need to process a lot of water, so the throughput, and then you have to have really robust detection.
Thank you.
And sorry, yeah.
Yeah, awesome. So we still having a new post coming up in the chat box. But we're just on top of time. We'll keep these two new questions noted and send to you like off our meeting. Thank you again, Nathalie, for such a thought-provoking and inspiring talk. And thank you to everyone for the engaging discussion. This brings us to the end of today's UNU-INWEH Science Talk. If you enjoyed the session, remember that all our previous talks are available on our website and YouTube channels at unu.edu/INWEH/science-talks. And please feel free to revisit or share them with your colleagues. We'll be back next week with another exciting presentation exploring new ideas at the intersection of water, environment, and health. Thank you all for joining us today, and we look forward to seeing you at the next Science Talk. Have a wonderful day.
Thank you very much. Thank you, everyone.